Hi, folks. Welcome and thank you for joining our latest webinar, Accelerating Product Design, a Case Study. I'm Misha St. Amand. I'm the head of marketing for JuliaHub. Today, I'm joined by our moderator, Dr. Ranjan Anantharaman at JuliaHub. He helps customers leverage modern computational methods through JuliaSim as a sales engineer. And today we are also joined by Brad Carman. We're very excited to have him here. He served as a mechanical engineer at Instron, specializing in system modeling with a focus on model and software development for the crash simulation system. And we're very happy to share that Brad has just joined JuliaHub to lead our consulting team, helping customers realize the power of modeling. A few notes before we kick things off and I turn things over to them. If you have any questions, please put them in the Q&A and we'll answer them during the webinar. And just to answer one question that always comes up, we will be sharing a recording of the webinar and any supporting materials with our registered attendees over the next few days. Now I'll turn things over to Ranjan and Brad.
Thanks, Misha. Well, it's great to see you here, Brad. I've had a great time working with you as a when you were the customer, but now we finally see you on the other side at JuliaHub. So welcome, on behalf of the company, and it's great to do this webinar with you. Do you want to say just a few words about what your interests and motivations are? And I know today's webinar is about model-based design, but what's your sort of view on sort of the importance of model-based design?
Yeah, sure. So yeah, I'm a huge fan of modeling and the power that it holds. I've been doing, modeling has been my go-to tool to solve engineering problems for my whole engineering career. And it's been kind of joked in the past that it's kind of like I'm doing magic in some cases, right? Because it is such a powerful tool that you're able to accelerate and solve problems so much faster when you're using modeling compared to using, I normally say trial and error, right? Like a lot of times we run to solving problems by just having an idea that sounds very, very good. Like, oh, this is a great idea. We've got this problem. I know we can fix it by just tweaking this or tweaking that. And you race to the shop or the lab and you give it a try and it doesn't work. And that is something that I've been burned by several times in the past, and that's why I've been turning to modeling time and time again, because it's just when that happens in modeling, you understand why it didn't work, right? And you get to see inside and know everything that's going on. Where when you're doing trial and error, you can only see the outsides. You can only see the bits that you're measuring. And so yeah, I've been a huge fan of this thing for a long time, and so yeah, that's
awesome. Thank you. Thanks. Thanks for that. Thanks for that, Brad. So maybe what I can do first as we get into really this webinar is about a case study that involves model-based design. But just to catch other folks up, perhaps we can. I'll do a little introduction of who we are, and then we can take it. We can sort of start getting into the specifics of the case study. So really, who are we, and what really is Julia? Julia is as we sort of describe it as a next generation scientific computing language. It's widely used at sort of many companies. The reason a lot of folks like Julia is because of this performance productivity, the sort of performance productivity trade-off, and Julia's strength is in trying to be performant while being productive at the same time. If you look at this little chart over here, which was released by the Chapel folks online, there's Julia has pretty low execution time, y-axis execution time, and has pretty small compressed code size, as you see, which is the x-axis over here. And so Julia sort of strikes that balance in a pretty good way, in terms of productivity and performance. And so we're a company that started by the creators of the Julia programming language. And so one of the advantages of having a language like that for scientific computing and modeling and simulation is you get really fast solvers. We've in our academic branches and in the open source, we've been working on really fast differential equation solvers that tend to be an order of magnitude or two orders of magnitude faster than the competition. And if you look at the little chart on the right, we call these work precision diagrams. So how much time, computational or wall clock time, do you need to spend to get to a particular precision? And the lines at the bottom of the charts over here are the Julia solver lines, which means you get a lot more precision for less time. So now so that's the sort of the open source or the academic foundation. But now we're a company that develops products, which sort of have this open source foundation. So the product we're sort of looking at today, and the one that the one that Brad is going to refer to, for his model-based design needs, it's called JuliaSim, and we call this scientific machine learning for our enterprise customers. So to give you a little brief about what scientific machine learning is, it sort of is a sort of confluence of the traditional modeling and simulation domain, which involves model building, solvers, controls, and sort of machine learning, which involves neural networks and the neural networks world in general, and involves automatic differentiation, backpropagation, and terms like those. And so what you get when you put both of these together is you get simulators that can be differentiated. And a huge advantage of that is that automatically accelerates design optimization. And design optimization, you might want to take fewer iterations, which you can do if you get gradients. You also get good surrogate models. You get inverse problems, of course, and gradient calculations help those inverse problems as well. You get equation discovery. So can you do a sort of a physics augmented model discovery approach? So you have a physics-based model, you have data, and you want to discover missing physics to append to the physical model, and use in sort of many low data contexts, which is common to a lot of our customers in the engineering domain. Today's webinar has a lot more to do with the traditional modeling and simulation world, a little less to do with the machine learning world, but what we try to do at JuliaSim is to sort of service the broad variety of needs there. And the way we do this is we do it based on an open source foundation with Julia and the SciML open source organization. And we have a design language called Modeling Toolkit, which we'll refer to extensively today. And Modeling Toolkit itself is open source, but we have a bunch of standard library components and proprietary components that are part of our JuliaSim offering, which helps you get quickly started with Modeling Toolkit and JuliaSim. And of course, on top of our models, we have our numerical methods, which are to do with model discovery, as I mentioned earlier, calibration, control, building surrogate models. So that's sort of the broad broad set of capabilities for JuliaSim. And if you guys have any questions about that, please put them in the chat and we'll address them. But perhaps very quickly, let's get into the actual topic of today's webinar, which is the case study that we published on our website. So this is just a little screen grab from our website, which you can find. And to sort of tee up Brad a little bit, we worked with Instron for many years, trying to service their modeling needs, and we ended up helping them. Accelerate their entire modeling process. So to talk about that a little bit, I will hand it over to Brad. So Brad, I think maybe the first question to ask is to tell us a little bit about the application. What really are we building a model of, and why do you need a model of it?
Sure. So yeah, this slide's perfect. So let's start with what this thing is. So the Instron makes this Catapult Crash Simulation System, which you can see in this picture here on the left. And it's this enormous hydraulic rocket launcher, essentially. And it is a 2.75 meganewton, a system that contains 2.57 meganewtons of force that is unleashed in the split second. And that unleashing of energy is actually precisely controlled so that you can reproduce any force waveform that you put into the system. So it's a programmable system, and it can reproduce this signal over and over again. And it's really just one of the most incredible machines I've ever seen. And so that's when I got introduced to this 10 years ago. I said, I have to work on this. This thing is just too cool. So what does it do? I'm sure you've all seen in the automotive commercials, they'll normally show like what's called a barrier crash, where they have the crash test dummies in a vehicle, and the car is accelerated and crashed into a wall, and you see an actual prototype vehicle getting crashed into a wall. So I show that in this diagram labeled real crash here. And in this case, you have a full vehicle, you have some dummies in it, and it gets accelerated to some velocity, and then it's normally there's a frontal crash, so it's just going straight into a barrier. And that barrier is, of course, inducing forces on the car and bringing it eventually to zero velocity. So those forces that are induced on the vehicle to bring it to rest, those are precisely controlled. Whenever they do one of these experiments, they have instrumentation all over the vehicle, thousands of measurements, lots of accelerometers. They're capturing everything about that crash. And the reason why they do that is because they're probably going to learn something very interesting from that crash. Maybe some specific part of the design failed to do what it was supposed to do, and they would very much like to iterate on that design and reproduce exactly that same crash. So that's where this system comes into play. So what it's able to do is replay that crash, and it does it on a sled. And so the advantage of having a sled is that you don't need to go ahead and build up an entire vehicle, which is going to end up getting destroyed. So as you can see in the picture there, that this customer is running a test with simply just a seat and a seat belt and one crash test dummy. So that is a huge savings, right? You can iterate your design on just the piece that you're focused on. And you can do it over and over and over again. And the thing that's a little bit interesting about this system is that it actually starts from zero velocity. So in the barrier crash, you start at velocity and end at zero velocity. In the crash simulation, you actually do the opposite. You start at zero and you end at the same velocity that the barrier crash would start at. And so that seems a little weird, but essentially what is happening is in the real crash, you've got the car crashing into the wall, and in the crash simulation, the wall is crashing into the car. And the thing is, velocity doesn't actually matter. The dummies or the occupants, they never can sense what velocity they're going. What you can sense and what matters and what is induced to the occupants is the forces, right? The forces is what's always important. So as long as you reproduce the same forces, then the critical bits that you're trying to measure and iterate on for a design, those are the things would be the same. So that's what I'm showing in the diagram there, is that the velocity, you start from zero, you end at 20, but the forces that are incurred, those are the same.
Nice, thank you. And you, if we understand you correctly, then it's the wall crashing into the specimen rather than the specimen crashing into the wall. Is that correct?
Exactly right. Yeah.
Okay. And in order to reproduce the forces of the crash. So can you comment a little bit on how one might even start designing a system like this? Like this looks pretty intimidating, doesn't it? Just as a system.
Yes. So That's a tricky question. This system is certainly an outcome of a lot of years of evolution. I think it started. I think the first system was built maybe 40 years ago. I mean, very, very long time ago. Was when, maybe even older than that. And so it's gone through a lot of years of experimental or design evolution, which is kind of like that trial and error process that I was talking about. And so it's a pretty slow moving thing. And eventually it gets to where it is now. And I can talk about some of the design changes that we made more recently. And of course, I'm going to be explaining how that was done with modeling rather than with trial and error.
Right, and as you say, this of course, this iterative process over time with trial and error, it's probably expensive, right? As it's just as on just to acquire the hardware to just set it up and run tests.
Yeah, exactly, and that experimental evolution over decades, essentially, it's like start small, right? The first system wasn't going to be 2.75 meganewtons. It was probably half a meganewton, right? And then the first step was like, okay, well, we need more force. So I'm sure what happened was they just made a bigger one. And that seems like probably a logical step, right? Just make it bigger. But every time I've witnessed us attempting to do something like that, there's always these real life consequences that you never thought of, right? So I wasn't there for the last, for the first decades of development of this system. I'm only speculating that that's how it's gone. But certainly in past projects, we've attempted to make a change, and you can see like, oh, that was a good idea on paper, but then you see that when you go to implement it, it actually takes a lot of time and massaging, right, to get it working right.
Awesome, thank you. And so, presumably you want to catch all of these and all of these edge cases that you referred to in simulation. So, which is why you went ahead and built a model. Is that correct?
Yeah. So, actually, if you want to go to the next slide.
Yeah. Oh, yeah. There we are.
I can explain why we ended up having a model in the first place. So the model actually originated not because of design purposes, but because of operation purposes. And it's kind of a long story how the system actually operates. But in short, as I said, it's a programmable system. So it's controlling the output. This 100 milliseconds window of force signal being played out. We have a controller that Instron produces that is actively controlling that. However, it's not actually controlling the acceleration output. It's only controlling the hydraulic valves of the system, which means there's this gap between the output of the system and what the controller is actively in charge of. So we call this an inner loop and an outer loop. So the outer loop is the acceleration or force output of the system that the customer would like it to do. And because we have this disconnect, what we have to do is figure out what is the signal that we send this controller that's going to give us that correct output of the system. And so that signal can be calculated from an algorithm. And the way the system operates in the past was that we would, and as this diagram is showing, you put in a desired force curve or acceleration curve to the software or to the algorithm, and it would come out with a signal that is a starter signal. And the system would have to go through a learning process. It'd have to do some iterations and physically run the system several times to get from that starter signal that was calculated to a more precise signal that's giving a much closer match to what the customer is asking for.
Right. That sounds a bit like a sort of an inverse problem, right? You have something and you're trying to find the input that gives you the right desired force.
Exactly right. And so this inverse problem is, in the past, was done physically, right? We had to actually iterate the system to do that. And that's problematic for a couple of reasons. One, it takes time to run the system. Charging 2.75 meganewtons of force takes some time. You have to reset the sled. Everything has to be set back into the initial state. It's a discontinuous system, right? So it fires and then it has to be reset. So that's problematic. So it takes time to do this. The other problem is that the algorithm that calculates the signal may not be fully aware that it produced something that may be impossible. It's a very complex system, and we have several valves in series that are being run to produce the output. And it's not always apparent that maybe one of those valves is being asked to do something that's impossible. Maybe it's being asked to be opened more than it can be, or, et cetera. So that's the other problem, is that a customer might be attempting to do something that actually is impossible. And the only way they can figure that out is that a lot of time spent iterating the system just to learn, like, oh, this is not going to work, right? So that's where the idea of having a model for the system originally came from, is that if we could reproduce that timely process of physically iterating the system, what if we just replaced the system with a model, and then we could do that with simulation, right? And so that's many years ago. That's where this whole idea of having a model for a system came from.
I see. So this is a model that's used for operations. Because every iteration will involve, as you said, operating the system, which would make it really, really slow. Whereas with the model, you can run the iterations quickly and then make the change in the system.
Right. And so in the end, that allowed us to confirm that the signal that we were calculating was correct. It allowed us to improve the signal generation. And as it turned out, it also made a lot of sense for us to go ahead and package this as a digital twin that we could give our customers, so that they could go ahead and check and optimize what they wanted to do with the system before they wasted a single minute of expensive lab time using the system.
Right. And so the first version of this model, as you mentioned, was sort of a hard-coded model, right? Could you say a little bit about what that model was?
Yeah. So many years ago, I built what I call the advanced model. Hard-coded. So I essentially just developed the whole model myself. And so I did it with a physics-based manner, and I'm using the Newton-Euler method so that I could get away from any kind of approximations. I wanted to have a fully nonlinear, fully physics-based parameterized model. And so, I did it in a way where I just basically hard-coded it. And that was fine for a system that is a static system, right? So system's already defined. We already know what it is, and we know what the parameters are of the system. So I could just kind of build the static model. And that worked great, right? It worked really well for exactly what I just described. However, as time evolved and requirements for the system got stronger, and we needed to evolve the system, that hard-coded model became hard to adapt to using for design purposes, right? And so that's when I started exploring, how can I do this better? How can I get the same benefits of this nonlinear physics-based model, but have it also be more flexible so I can make changes to it? And
so you needed to make the next generation of your model, for which you needed the next generation of modeling software.
Exactly. So that's when I went searching for some modeling, better modeling tools. and I discovered the acausal modeling. I was also in search of speed, because at the same time, Instron was also coming out with a new controller that was a much faster controller running at 10 kilohertz. So I was motivated to not just get a better modeling tool, but a tool that could give me much faster runtimes than I could get when I just write the whole thing myself, right?
Right. So the business use case in many ways was to take advantage of the new hardware that is available, right? And incorporate that into the new design. Is that
Yeah,
how you describe it?
trying to answer the question. Customers are asking for more challenging signals that are more dynamic, with higher forces, and how do we answer that question, right? Of what do we need to change about our system in order to achieve what our customers are asking us for, right?
Right. And so you started using Julia and JuliaSim for, you ported the model to Julia and JuliaSim, and this happened. Was that 2022 or was that 2020, Brad? When did you first start perhaps using Julia?
Yeah, I think it was around 2020. It was definitely when the pandemic hit and things kind of slowed down a little bit. I decided that I was going to go ahead and just like kick the ladder out. And since I had a little bit of time, I was just going to try to transition everything to Julia and just make it work. And at the time, I knew that Julia had the speed. And so that was kind of my first motivating factor. But I ended up getting lucky and learning that there were a lot of other big advantages that I got from moving to Julia.
Right. And so I guess maybe the first advantage of maybe to speak about is just the speed, right? So you ported the model over to Julia, and it ended up being faster, that you could actually use it for design, or in this case, design optimization.
Yeah. So the advantage that I got with speed from Julia was kind of a two-factor thing. So the first factor was the dual language problem, right? That the classic, what is referred to as the dual language problem. So that helped a bit. That I didn't need to worry.
Sorry to interrupt you, Brad, but just for our audience here, and again, the audience should feel free to ask questions, but just to recount for the audience here, what is sort of the dual language problem in your eyes?
Right. So I think the classic definition of it is that a lot of tools need to be converted to C to be able to be compiled in C to get those fast runtimes, or Fortran maybe, because those are the classic languages that give you that fast performance, computing performance, which means nobody wants to work in those tools because they're very cumbersome coding tools. You would rather work in a tool that's like actually designed for doing math algorithms or modeling or whatnot, right? So that's kind of the dual language problem, the classic definition of it. And so that was definitely something that I was seeking, because it slows down development every time you want to. Every time you finish making a change to your model, and then you want to go ahead and run it through a lot of different cases, you're always having to do that conversion and compilation in a different language, right? But there's another dual language problem that I also refer to, is that there's also a need to use another language in a lot of cases for doing useful, I'll say useful stuff with your model, because building a model is not the end, right? If you have a simulation, that's nice. You can run a simulation and get some information out of it, but normally you want to use that simulation in some kind of algorithm or some kind of process or software or whatever, right? You want to do something with that simulation. So there's always been this also another dual language problem where you kind of have to decide where does the model end and where do you do something with that with another language, something useful with it. And so I used to have to kind of try to figure out where was that line and what was I going to do in like, for example, I was doing a lot in C# because I was eventually porting the model into software. I was having to kind of juggle the two languages, right? And that's challenging, right? You got to be very organized, and it can really slow things down, especially when you're in the process of development and trying to come up with a whole new system. So Julia solved that problem, right? Because it's a full-featured language that it doesn't really have any barriers with what it can do. Julia can do just as much power as any other full-featured language. So I didn't have to like live in that world anymore. That was another motivating factor for me, was that I could build my model in Julia and then do everything I wanted to do with that model in the same language, and it made it very efficient development process for me.
Right. And the dichotomy you're referring to is sort of the language of model design and the language of model deployment, and how sort of Julia merged that gap. So we have a question from the audience, okay, which perhaps we'll answer a little bit later. But maybe actually when we discuss your slide here, this is a good segue. Do you so now that you had the model in Julia, could you say a little bit about how how you started to use that model? And
yeah, sure thing. So what this slide speaks to is, again, like I was saying, we had demands from customers for more performance. I mean, it's a pretty typical story that any product is going to be, over time, customers are going to want more performance for less cost, right? That's a pretty typical story. And so we were looking at how could we optimize our design to give the performance, but simplify the system so that we could reduce costs, right? It's a pretty typical story for a design iteration. So the trick with the Catapult, though, is that optimizing the design of the Catapult requires to get one data point for a loss function, for example, for an optimization process, is quite a large simulation, actually. Because what needs to happen is we need to simulate a real life system with real life errors. Because what's really critical with a system like this is not just that it can produce the force signal, but how well it can produce the force signal, right? So we have to run through the same process that I described in the previous slide, but we have to do that in simulation, and we have to do it close to like the real life conditions, which means we have to get the system in its preconditioned state. And what that means is before the system fires, it goes through a long process to kind of prepare itself, basically. Like the valves are getting themselves into position, and then the system fires. So that means I'm not just simulating a 100 millisecond window, I'm simulating a window that's more like seconds of time, and I'm having to do it for several iterations and several repeats. And so that's why it says here, one data point took like something like 10 minutes using the previous model that I had built. And that's exactly why, because it's just, you had to run it so many times and you had to add all that extra time to it and all that extra complexity to it. So that was another motive, right? That was one of the reasons why I was motivated to get that increased speed, right? Because in order to do a design optimization like this, and I had to do that thousands of times, it wasn't going to work if it took 10 minutes to get one data point. Right.
So do you so this of course like is the speed benefit that you're referring to, but like just to comment a little bit on the model itself, were any of the components, so this is a multi-physics component based simulation, a system simulation, right? Were any of the components sort of like finite element discretize, finite volume discretize? Like, what did you use? Any like other third-party tools to design some of the component? Do you have, or is it all in JuliaSim?
No, it's all in JuliaSim. And it's the model is primarily 1D type simulation. There's a little bit more complexity to that answer, but it's all kind of 1D stuff that you don't need to do full simulation type stuff to do a system model. And then, there's a lot of art in that with system modeling is how do you simplify something that would normally take a full 3D simulation to how do you convert that to a 1D kind of thing.
Okay. Thanks. There's a question here on the chat about using sort of multi-fidelity. The question basically asks whether have you used sort of multi-fidelity models and deployed them in optimization loops where some of the components are a finite element or finite volume simulations, and the answer is yes. Just to sort of, it's a slight aside, but we in our HVAC library, for example, the heat exchangers and stuff are finite volume discretized and so on. And so we couple them with other components that are not discretized using finite element or finite volume. So yeah, the answer is yes, and of course we do design optimization of those types of systems as well. So just to answer the question that has come so far. Brad, just to move on a little bit, like actually, could you say a little, like, could you comment a little bit about the 500x? Like, could you repeat a little bit about like why, where the 500x really came from? Like, would you be able to break that down a little bit for us?
Sure. So the first part is moving to acausal modeling. And a tool like JuliaSim, I get a lot of that for free because previously what I was doing, I didn't get any optimization or simplification. I was kind of just solving the entire set of equations all together without any simplification. But with the JuliaSim, you get this nice automatic simplification of the problem, where you get this great reduction of how many equations are being solved, for example. So that's the first part of it. The second part is the differential equations.jl, giving just excellent performance right out of the box. And then one other cool thing that I did with differential equations was use the composite solver. I believe that's what it's called.
Yeah,
where you can right. So you can mix solvers, and so as I had described a second ago, there's this few seconds of preconditioning of the simulation, and then there's the part where the system actually fires. And to the point of view of the solver, those are two very different problems, even though you're solving the same problem. Because in the preconditioning, everything's moving pretty slowly. So a much faster but less stiff solver could handle that bit, and then it could switch over to a solver that's a bit slower but can handle a nonlinear, very stiff problem in a much better way. So that was a nice thing that I could do, where I could like really accelerate the parts of the model that were slow in real life, but fast in simulation, right?
Course.
And those things together, and that was it. Like I had something that was really, really cooking.
Thank you. That makes a lot of sense. What could just as we wrap this particular segment up, do you want to could you comment a little bit on your developer experience with Julia and JuliaSim? How hopefully writing the model was not a painful process, as it can be sometimes.
Yeah, so So to tell the story a little bit more, what we were after here was how could we simplify our system, right? And what I'm showing in the diagram there is that our current system, or I guess I could say our full-blown system, is kind of two products in one. It has a high gain and a low gain mode, which allows us to be able to do lower force but higher precision signals, or higher force, higher dynamic signals. And you can switch modes for whatever needs you have. So what we were after here in this case study and in this optimization process was, could we shift that more the mechanical design of the system to the controller? So could we have that high gain, low gain mix by just using by putting more of the load on the controller and less load on the actual mechanical design of the system? And so, yeah, to answer your question, to make changes like that in an acausal model, where I'm like taking bits out and moving bits around, it's a breeze, because acausal modeling is more analogous to real life. You're building up components that you're connecting to each other, just like in real life you're connecting bits and pieces together. So it made it much more of an achievable thing to be able to organize the model where I have components and I'm able to swap in and out. Whereas if I'm just doing this in a flat model with just equations, that becomes very, very tedious and hard to do something like that.
And yeah, thanks for bringing that up. Of course, this 500x wasn't just an experiment. This led to a completely new design, which
Right.
we're referring to here as a Catapult Lite.
Right. And so this is the kind of thing, going through an optimization like this, as it shows here on the slide, it took, a very long iterative process using an optimization algorithm to land on that final optimal design, right? And that shows you right there that it just would have been impossible to do something like this in real life, to physically tweak a system that is discontinuous like this system, and to continue trying and trying and trying and trying. It just, we never would have gotten there, right? So being able to do this in simulation was a must.
Yeah, I mean, it's the power of acausal modeling and model-based design.
Right.
Do you just, again, just so we are keeping time, do you want to quickly comment on the developer experience before we move on to the next section here?
So the development experience was, I would say, because of what I was referring to before, with the ability to stay all in one language, was quite nice. So I was able to quickly tweak the model, but then run it directly right to the algorithm that I was applying it to see if what I was doing made any sense, right? So that was really nice. There's also a lot of nice things about Julia that also made the development experience good, where the fact that it's modular and you can have a nice flow of an organization of your code, where you can have unit tests for each little module, and versioning of all the modules. You could stay organized and be sure that, what's the right word I want to use here? It's just, it was a nice modern development process that really helped accelerate things, because I wasn't spending tons of time trying to figure out why something wasn't working, because I had that good foundation that Julia offers.
That sounds great. So just so if the audience, if folks have questions, feel free to chime in. So that's sort of the first part of what we wanted to talk about, just your experience in general. But I think the other part that maybe we want to maybe comment on is, hey, so do you if I'm an engineer in some company X, and I'm looking at this and I'm like, okay, I want to be able to do the same thing. I'm trying to see how your experience is sort of transferable to my team and my company. So most of the
Sure.
things that you seem to suggest does not seem to be, you didn't have to do anything too specific for just your project, right? You could transfer it to other projects, and so can other folks at other companies. Is that a fair thing?
For sure. This is a complex system. And so I think a lot of times it seems like, oh, okay, this Julia or JuliaSim is needed for something like this, and you don't really need it for something simple. But honestly, the foundation, the fundamentals, it's all the same. Building up a hydraulic model is built up from very simple fundamental components that it's, I would say 90% of this model is built up from foundation library, right? Or from the standard library. Yeah, fundamental components was what I was trying to say. It's pipes, it's volumes, it's masses, it's springs, right? It looks complex from when you're standing back and looking at it, but when you look under the hood, what you're finding is it's just all those fundamental bits all connected to each other.
Yeah, absolutely. And so there's also, as you said, a lot of components that you use for fundamental components, right? And
right.
A large part of some fundamental components at JuliaSim are already open source in the modeling toolkit standard library. So really, you could get really far with a lot of fundamental components.
Absolutely.
Yeah, and starting to leverage our tools. Did you get a chance to sort of, while you were at Instron, replicate this type of success at other projects?
Absolutely. So this was my focus at Instron. I think this is where I spent a great deal of my time. But their Instron makes all kinds of different testing equipment. This is definitely our biggest machine that we make, but we make all kinds of different tensile testing machines, material testing machines, automotive structural testing machines, and certainly there were lots of projects where there was a problem that needed to be solved, some kind of there was a mystery to be solved, right? And this is where my name would normally come up, because I was the guy that had that magic that I could use. So the magic was just modeling, right? Every time it was, let's take a look at what's happening, let's build a model of it. And that's another time when the acausal modeling was just really useful, because it really, you can build up a fairly complex system very quickly by you just connecting things together, right? And so yeah, this story is a very complex story, but the same fundamentals of it played out several times in my time at Instron.
That's
sure.
very cool. And one of my favorite terms that you use, is what you often refer to as model-based innovation, to be able to advance the next generation of products just by building system simulations of them.
Right. Yeah, and I think when I refer to model-based innovation, what I'm talking about is kind of what we're showing here on the slide is sometimes to get a big leap forward doesn't require coming up with a completely new idea. Sometimes all you actually need to do is tweak parameters. And it may not be intuitive what those parameters are that need to be tweaked and what they should be tweaked to. So if you have a model, by definition, you essentially have identified what are the variables and what are the parameters. What are the knobs that you have to turn to get the output of that design, whatever it is, right? And so when you have that model, you can now ask the computer to run an optimization study and turn those knobs for you and come out with what is a better design. I think a lot of times we end up building a product that is at a state of where it works, because that's always the first goal, right? If we're ever trying to solve a problem for a customer, we build that thing, it works, and we sell it. But we don't start from a point where we're making it optimized, right? I mean, the very first car that was made wasn't made optimally. It was just, once I had it working, it was great, right? Sell it. But then now you have this opportunity to take a look at it. How can you make it even better? And in a lot of cases, that really just means you're just tweaking things. And you can actually sometimes get a huge performance improvement by just making small adjustments to the parameters of the system. So that's what I call model-based innovation.
That's fascinating. So I know we have a little bit about about how about model-based innovation in the previous slides here, but we've spoken about that quite a bit. So I'm just going to skip those. But I do want to leave our audience here before we conclude with a call to action. So model-based innovation is sort of, as I understand it correctly, sort of a personal mission for you as well, Brad, which is why you ended up joining us over here from your time at Instron, at JuliaHub. Do you want to say a little bit about how this sort of thing aligns with your personal mission? What it is you're going to be doing at JuliaHub now?
Yeah, so I'm very excited to have joined the team, and yeah, like you said, my mission in life for certainly is model-based innovation, and I because I see the power that it's brought in all those past examples, I'm very excited to do that, to help share that experience, right, and to help other companies experience that as well. So I am starting by leading the consulting team, where we'll be able to offer that service, and I think what we're a potential customer would be someone who is struggling to advance their product. They have some kind of problem, and you might be a potential in need of modeling. If you ask yourself this simple question, are you doing trial and error to advance your whatever problem you're trying to solve, right? There is a better way, and that way is with modeling, right?
Oh, and if I might add that, I don't want to put too many words in your mouth, Brad, but if you're already doing modeling today and you want to do it better, you could perhaps talk to us and get on sort of the next generation of modeling tools as well. But
yeah, absolutely.
So sorry, so Brad is going to be working with and sort of expanding the use of JuliaSim, offering modeling services. And if this is the kind of story that you'd like replicated at your company, do get in touch with us at sales@JuliaHub.com. You can also apply for access to JuliaSim through our preview program, which you could go ahead and you can see a little screenshot over there. But if you just Google JuliaSim, you'll be able to click a button on the website and which will take you to our preview program. Yeah, that's sort of a little call to action. Brad, any final thoughts before we open the floor to questions?
No, I've really enjoyed being interviewed by you. This has been a lot of fun. So I'm happy to get any questions if there are any.
I'm glad, Brad, you had fun, Brad. So I'll hand it over to you, Misha, to see if there are any questions.
We don't have any questions, and since we're so close to time, I would suggest that we wrap up and folks can reach out to us directly if you have any additional questions. You can reach out to our follow-up email, or I'll include Ranjan and Brad's email addresses as well if there are follow-ups to this. I'd like to thank everybody for attending. Ranjan, thank you for moderating, and Brad, thank you for bringing your wealth of experience to share your story with us. It's very much appreciated.
Yeah, my pleasure.
Thanks for everyone who attended. We look forward to seeing you in another upcoming webinar. Thanks, everybody.
Thanks all. Thanks, Brad.
Yeah.